there can be problems with GoToMeeting, and there is always problems with, WebEx and stuff like that. Usually it's not a question of if something will go wrong, but when something will go wrong. And interestingly enough, that is exactly our experience of running Kubernetes on AWS. It's not a question of if something will go wrong, but when something will go wrong. And sometimes what will go wrong. Hi everyone, my name is Shrinand Javadekar. I am a software engineer at Applatix, and I'm really excited about talking to you about what we have been doing with Kubernetes and running Kubernetes on AWS at scale and the kind of problems we ran into. To talk more about this, I also have a colleague of mine here with me, Ahbinav.
Hi, I'm Ahbinav. One of the things that happens with Kubernetes, for example, that Shri mentioned that things go wrong, and it also goes wrong because Kubernetes is actually running on the cloud. In our case, it's running on AWS, and so a lot of times we find that it is actually this interaction between Kubernetes and AWS which results in all these interesting and challenging situations that we've had to work on over the last year or so.
So before we get into the crux of Kubernetes on AWS, a quick word about what Applatix does. So at Applatix, we are building a platform for building and running containerized applications in cloud. We are building this platform on top of Kubernetes. So Kubernetes is like kind of the heart and soul of many things that we do. And the mission really is to simplify the journey to cloud using three things. Infrastructure automation, so whether it is provisioning resources, managing cloud resources, volumes, EC2 instances, network configuration, VPCs, what have you, automating all of that infrastructure, making sure that it really does what it's supposed to do is an integral part of what we do. End-to-end DevOps workflows. So yes, Kubernetes is at the heart of what we do. Kubernetes can schedule and run containers, but running one container at any point in time is not going to be very useful. What you typically want is a sequence of steps that you want to run so as to achieve an end goal. These steps could be serial or parallel. So on an Applatix cluster, you get this workflow engine where you can define what steps you want to run, and these steps could be sequential and parallel, and each of these steps is a container. And monitoring, audit, and governance. So when it comes to consuming cloud resources, one of the fundamental problems people face is visibility into what is happening. Who's running my using my cloud resources? What are they using it for? How much am I paying for it? Money is a first-class citizen of an Applatix cluster. So you can see exactly what money you're spending, how much money you're spending, and it's not just being able to see where the money is going, but make it actionable. You can say that I can run a workflow or run a particular workflow only if it does not exceed 10 cents or something like that. It's an actionable resource. So having said all of this is what we do. It's really cool. But let's just jump straight into running Kubernetes on AWS.
Right, so let me just go over the outline of the talk, and it's interesting that the outline of this talk will actually follow the journey that we took when we were building our software using Kubernetes. And so it's like a story that we're going to tell about how we hit these problems and how we solve them. And actually this talk will focus more on the problem set and one set of solutions that we preferred in some cases, but mostly we wanted to share our experiences with like all the roadblocks that we hit along the way, and hopefully you can avoid some of them. So first we started off with a problem that we ran out of memory, and on a cloud you're running in a memory constrained environment. So we hit some problems with out of memory issues. Then we ran to the next set of problems where AWS actually had some limits, and so we hit those limits. A lot of interesting interactions between the two. Subsequently, we started hitting problems with volumes, and then as we hit those volumes, we started thinking about sort of our operational strategy and how do we sort of optimize the use of our resources. So we call that cloud hygiene. And lastly, we talk about a very interesting thing that we use autoscaling groups for. It's an Amazon concept, and we use that for improving our reliability and scalability. And I'll pass it back to Mr. Reliable over here.
I hope my manager is listening to this, Mr. Reliable. So, this is about a year and a half ago. We got over the initial barrier of setting up Kubernetes on AWS. And once we went past this barrier, we started running these long-running tests on this cluster. These tests were something pretty basic actually. We were trying to run hundreds of containers per minute, or rather hundreds of pods per minute, And some of these pods were also provisioning other Kubernetes resources, such as persistent volumes, PVs or PVCs. And there was a lot of churn and a lot of things happening in the Kubernetes cluster.
So yeah, just let me quickly ask you this question. You mentioned pods and containers and PVs and PVCs. Can you elaborate a little bit about what these concepts are?
Yeah, good question. So in Kubernetes, a pod is basically a wrapper around one or more containers. It's a way of telling Kubernetes that here are my n containers or n containers, and Kubernetes will take this and run these containers together on one instance or one VM or one compute instance at any point in time. Mm-hmm. PVs stand for physical volumes. So think about them as typically as disks for storing your persisting your data, and PVCs are persistent volume claims. The way I think about PVs and PVCs is similar to how there are files and file handles. Files are things which are actually they are on physical media, and there's actual data that's stored in them. File handles is basically a way to access the file. It's an in-memory concept. It's like one way in which a process can say that, hey, I'm going to use this, or I am using this file. So PVCs are a way in which you can claim a persistent volume.
Right. Yeah. So pods and PVs and PVCs, I think, are very useful Kubernetes constructs. We definitely love using these abstractions that Kubernetes provides for us. So
yeah. So we had this workload. Basically, we had a Kubernetes cluster in which we were hammering this cluster with hundreds of pods per minute. Some of them using creating PVs and PVCs. And when we ran this cluster overnight, we found that the next day morning the cluster was not accessible. We had to go and SSH into the Kubernetes master to see what is really going wrong. And it turns out that etcd was getting killed. So etcd is this component used by the Kubernetes master for storing all the metadata for the Kubernetes cluster. Which nodes form part of the Kubernetes cluster? What are the pods that are currently running in the Kubernetes cluster? What is the configuration for each of these pods? What are the events that are happening? All the events for every pod and every node get streamed to etcd, and etcd stores them in memory and on disk. So it has a lot of in-memory data, and it has a bunch of it does a good job of trying to flush out a lot of the data as it comes in onto disk. But as you can imagine, it has a finite amount of memory. Some of the as events and new pods keep coming in, this memory starts getting used. And if the rate at which this new events keep coming in is higher than the rate at which data is being flushed onto disk, then etcd sooner or later is going to run out of memory. Not to mention, it also has snapshots. So it keeps a lot of these snapshots in memory so that it can access them whenever someone wants to get the information about a pod that was started like 3 days ago or something like that. So a lot of this data is is stored in etcd in memory. And sooner we found that, or after running for a few hours, etcd was running out of memory. Not only is it a problem with etcd, but there are other services that run on the Kubernetes master, such as the API server, kube controller manager. These interact with etcd for, again, storing some metadata about the cluster or getting some information about a pod. And when etcd is down, then these other services also kind of get into a bad state, causing them to get killed at some point in time. So eventually, it all came down to the root cause being that etcd was running out of memory. So what did we do about this? So etcd has some good documentation about this. They do mention that snapshots actually consume a lot of memory for storing some metadata, and there is a parameter called snapshot count. And this snapshot count, I think the default is 10,000. And if you don't care about snapshots, or if you're okay with a little more, with a little slower, etcd being a little slower, you can dial down this snapshot count parameter. So we dialed it down from 10,000 to 1,000. So suddenly the amount of memory that etcd had was larger than what it typically had, and it kind of enabled us to kind of, it had enough leeway, enough legroom for consuming these spikes.
Right. So another interesting thing about why we sort of one of the reasons Shri mentioned is that we definitely are testing our system, and so we are hammering it with lots of containers. But another reason we are doing that is because our workflow actually, so as Shri mentioned, that we have this workflow concept which boils down into a sequence of steps, and each step actually ends up being a pod. And each pod ends up being one or more containers, where one of the containers is the container the user wants to run, and other containers are sort of our system components, which actually create an environment for this container to run and do other interesting things like artifact collection and stuff like that. And so we definitely are testing the system for this high churn, where users are creating workflows, and each of these workflows is generating lots of pods and containers. And so we want to make sure that the system, that our cluster, is actually resilient to that kind of workload.
Yeah. So kills was one of the first problems that we ran into. We dialed down the snapshot count parameter, but as I mentioned earlier, this is one solution. The focus of this talk is going to be on problems, and these are the problems we ran into. There might be other solutions to these problems depending on your environment, depending on the workload. The same solution may or may not apply, but this is what we did. So once we got past these kills, we moved on. So we now had this cluster, or tried to run this cluster for, again, long-running tests, hammering it. And we ran into this second set of problems called AWS Limits. So any and every resource on AWS is actually available as a REST endpoint. So you can make an HTTP request to create an instance, or to query the status of an instance, or to create a VPC, what have you. And all these REST APIs that AWS has, there are limits on how many of these APIs you can query or you can call every second. Or there is a well-defined rate at which you can make these API calls. And when we had this large cluster, which was kind of making continuous AWS API calls for creating new volumes, or creating new instances, or querying the status of instances, sooner we started realizing that there were some of these calls, or a large number of these calls, suddenly would fail with an HTTP 500 error. And the error message that AWS returns was that you are exceeding the rate at which you can make these API calls. And this was an interesting one, because there is this notion of this vast set of resources that you have at your disposal, but well, sometimes it's not exactly true. There are these well-defined API rate limits that we ran into. Not just were there rate limits, but there is also a cap on the maximum number of resources that you can use. And this is applicable to pretty much every resource that you have on AWS. So whether it is VPCs, subnets, launch configurations, S3 buckets, IAM rules, whatever. So something like VPCs you can have only 20 of them per account. Yes, you can make a request to AWS and they can bump up this number, but it goes from say 20 to 50 or something like that. Right. So we ran into rate limits, so we couldn't query the status of some of the resources that we had provisioned. We ran into these caps, so we couldn't create a new cluster because they said that, hey, your new cluster requires a new VPC, but you've already run out of the VPCs that you already have. And yes, there is some way in which we could do better automation of this. We could do things such as create multiple clusters in the same VPC and so on, or use S3 buckets such that multiple clusters use the same S3 bucket. But there was also a bunch of things that we could do from an operations perspective to make the situation better, right?
So another interesting thing over there is sort of the intersection between the rate limits that happen on AWS and Kubernetes. So as soon as you hit these rate limits, like so for example, you're trying to do a describe volume, or you're trying to do an attach volume, which is like a API call on AWS. What happens is if you hit the rate limit over there, then Kubernetes will realize that, okay, that's, you're hitting this rate limit, and it actually generates an event. So it'll generate an event that I tried to attach a volume and it failed, or I tried to do this and it failed. And guess where these events are going? These events are actually going in at CD. So now on a heavily loaded system, and if we had, let's say, not tuned those parameters, we are generating lots of churn in the system. That churn in the system is generating these rate limits, and that rate limit is now actually creating even more events on etcd. So that is like a snowball or a cascade of problems that were hitting us early on. So that was it's sort of just interesting to see how like one thing led to another, and how they kind of folded upon each other in terms of how that played out.
Yeah, this was an interesting case where AWS rate limits or errors on AWS caused more and more errors on Kubernetes, right, causing them to kind of go in this really bad cycle of events.
Right.
So as I mentioned, like there was some scope here for automation and better engineering, but there was also a bunch of things that we could do at an operations level. So this is where we kind of focused on quite a bit. things such as judicious use of resources. We were making sure that we provision clusters that we really need. If you don't need resources, don't provision them. Or make sure we don't hit those caps. Multiple accounts. So we realized that the rate limits and the cap on the resources is applicable on a per account basis. So one good thing to do was to kind of create a separate account every time we kind of hit this, so that we have this new fresh set of rate limits to go to use, or new caps to kind of figure out. So multiple accounts was good. It also helped us in a way where we could create multiple accounts, one for dev, one for demos, one for production, and so on.
It's always very good to have different accounts for demo and development, because you don't want your developers messing up your demos.
Deleting unused resources, again, good to do regardless. Helped us to avoid hitting those caps. At the same time, kept our costs down, so it was good to do that. Tagging all resources. So AWS has this great notion of tagging any and every resource that you can use. So one rule of thumb was to kind of tag every resource with a tag called Kubernetes cluster, and the value of it was the name of the cluster. So at any point in time, we were able to go and figure out what resources any cluster is consuming. If we were to delete a cluster, we would go ahead and delete all the resources which had that tag. So it made it that much easier to delete all resources that were not used. So once we got past this, so we said, okay, there are rate limits. Let's just have good operations, be good citizens, create other accounts, and got past that problem. Then we landed up in this whole other big set of issues called volume problems or volume issues. And I have a big asterisk sign here which says under development, because volumes and persistence is actually an area under active development. Like the Kubernetes community mentions or acknowledges the fact that this is an area that needs more work, or that needed more work, and has been actively doing a lot of work on it, fixing bugs, adding new features, so that people who want to run stateful applications on Kubernetes can do this without having to worry about a bunch of these problems. But having said that, as we said, we wanted to focus on the problems that we ran into, and these might be experiments that you do, and figure out whether these volume problems happen in your environments as well.
Right. Another thing to add flavor over there is basically when we started using Kubernetes persistent volumes, this was during the 1.3 timeframe, and this is all just new and alpha features. So we use this concept called dynamic storage provisioner, and that's a Kubernetes construct where what Kubernetes does for you is you can just say in your specification that, hey, I want a 10 gig volume, and then Kubernetes is actually going to go figure out how to create a 10 gig EBS volume, and then also attaches that volume to your container. So that's all very useful, but also very new at that point of time. So just some of the problems that we hit over there are definitely getting solved along the way.
Exactly.
But we also had to find interesting ways to work around those problems while we were trying to use that feature.
Absolutely. So what kind of problems did we really run into? The first one that we saw was volumes getting attached to wrong pods. So we had two pods, a Redis pod and a Kafka pod. Each of these were using one volume each. So the Redis pod was using a Redis volume. It was running on one instance. The Kafka pod was using one Kafka, was using one volume. It was running on one other EC2 instance. At some point, these two EC2 instances died, whether we killed them ourselves or whether AWS killed them because of some hardware errors, whatever. But the instances died. New instances come up, and these two pods get scheduled on these two different instances. However, when these pods moved onto the new instances, what we found was that the Redis pod was using the Kafka volume and the Kafka pod was using the Redis volume. Now, thankfully, both of these processes or both of these services create their own directories and write data in their own directories. But if they had not done that, it could have actually resulted in data corruption. And which was like something really interesting for us to see. And when we thought about this, one solution that we came up with for this problem was to use init containers.
Right. And yeah, so thankfully, actually, we didn't get any data corruption over there. We got really lucky. But so init containers is this interesting concept in Kubernetes where you can define a container that actually runs before your main container. And if that init container succeeds, only then the main container is run. This was also an alpha feature back then. I think it has moved to beta now. But what we did was we used this init container to generate sort of a signature check mechanism where if the first time this volume was being attached, then we would generate a signature that was specific to the kind of data that was being written to. For example, Kafka would generate a different signature than readers. Right. And so then subsequently, whenever this pod would get moved because of an unfortunate event of a EC2 instance failure or something like that, we would ensure that we would only write to the volume. We would only start using the volume if that signature actually matched what we had. And so this was really useful for us to ensure that in the worst case, we do not have any data corruption, given the fact that we saw this problem. The good thing is that we did not see this problem a whole lot. Yeah. We saw this a few times, but those few times were enough for us to take a step back and say that we need to add some metric, we need to add some reliability on top of it.
Yeah, you can never be too careful with data. So I'm sure this problem would get fixed on the Kubernetes side at some point. Right. But regardless, I think it's always good to have
a check.
Yeah, it's always good to have a check, and better safe than sorry. Right. The second problem we ran into was failure to unmount and detach volumes. So this again had to do with moving pods from one instance to another. Right. So we had this case where there was a pod, it was using a volume, and this pod for some reason moved from one instance to another, whether this was because the pod died or for whatever reason. The Kubernetes master decided that this pod should run on a different instance, and it scheduled the pod on that instance. But what happened is the volume that this pod was using did not move with it. So we had two instances, and the pod was scheduled on one instance, but the volume that this pod was supposed to use kept on being attached and mounted on this previous instance, and the pod was just waiting there forever for this volume to come and get attached to it. And this wait was basically endless. This was like an infinite wait, and what we had to do in this case was to manually unmount and detach that volume so that that Kubernetes can then attach it to the correct node and then make that pod kind of alive again. So in this case, the interesting part was that even if everything was there was still some downtime.
Right. And interestingly, what happened over here was this actually happened a lot to us. And one of the reasons it happened a lot to us was we actually were using volumes as a way of caching. And so these volumes were actually moving from one step of the workflow to another step of another workflow. And we were using this for like some interesting caching behavior. But regardless, we were actually able to see this a lot. Like this problem was like a daily occurrence kind of problem. And so we actually built a lot of reliability around that to make sure that if the moment we detect this problem, we took corrective action.
Yeah. And I mean, pods being there but not being able to run is actually really
it's waste of dollars.
Yeah, it's waste of dollars, absolutely. Runaway volumes because create and tag were two different API calls. So yeah, so this is more of a thing on the AWS side. So we wanted a volume, and as I mentioned earlier, one of the good things about using AWS resources is to tag them. So we wanted to create a volume, tag it, and then start consuming it. But the way AWS has its APIs, create and tag were two different API calls. So you make a call to create, you go to AWS and say that I want a volume of say 10 gigs. It will create a volume, give you back a volume ID, and then you make a second call saying that for this volume ID, create a tag called Kubernetes cluster, and here is the key and value. But because these two are two different API calls, it's very possible that after the create call succeeds, but before the tagging call actually is made, the process dies or there's a network partition or something goes wrong. And the tagging never happened.
Right.
So now we had created this volume, but it was never used. Right. And kind of these volumes just kept on piling up, and at some point we hit those caps that I mentioned earlier. Right. So this was a problem on the AWS side more than the Kubernetes side.
Right. And it was interesting actually, I actually just remembered that what really happened over here was also sort of a cascade of problems. So if you remember from earlier when we were ooming at CD, it was actually causing the kube controller, which is one of the components that actually creates these volumes, to also go a little crazy. I think it was ooming as well. So while this cluster was being hammered and was trying to create volumes, these create and tag calls were getting separated out because the master, the kube controller would actually die in the middle. Right? So now you had this like cascade of problems that was getting worse and worse. So another thing that sort of is a full circle over here, right?
Yeah, when things go wrong.
Murphy's Law.
Yeah. All right. So By the way, recently AWS, I believe, has solved this problem by making create and tagging calls to kind of be fused together. You can make a single call to create a volume and tag it at the same time, which is a good thing, which would go a great deal in not running into these problems again. And then the last one, created volumes didn't actually exist. Yes, this sounds a little blasphemous, but the thing is, yes, this happened only twice. So in 1.5 years, it has happened twice, but it did happen. What we saw was that in a couple of these instances, we created a volume, we got back a volume ID, which meant that AWS says that, hey, here is your volume ID, your call succeeded, and use this volume ID subsequently for attaching the volume, mounting it, and start using it. But when we actually tried to attach the volume, AWS said, hey, this volume doesn't exist. And we made sure that there were no calls to delete the volume in between after create. So between create and attach, there was nothing else that happened, but for some reason, this volume didn't show up. And we actually have...
Because we were sure you would not believe us, right? So we have screenshots of this.
Yes. So AWS has this thing called CloudTrail, with which you can actually go ahead and look at the exact sequence of events that happened on any resource. So we have this CloudTrail log here for one particular resource. So on 21st of February this year, you can see these last two lines which show create volume and create tags. So these two calls happened at about 12:03 p.m. This create volume call actually succeeded and returned an an EBS volume. So you can see this vol-040 blah blah blah. And then subsequently, the only calls that happened on this volume were attach volume, and all these attach volume calls failed. And in this one log that I have expanded, you can see the error code, and the error code says invalid volume not found. So this volume was not found on AWS said it could not find this volume, but the call to create had succeeded. So, it kind of leaves you nowhere. The one call succeeded, the other one didn't, and we kind of trust AWS or trust a cloud provider to do the right thing, but actually may not be true all the time. And one way around this would be to just kind of, when you start using a volume, don't just assume that the call to create succeeded means the volume is there. Make sure that it's really there. Maybe attach it, mount it, read, write something, and only then, once all of these things succeed, then you would know that a volume is actually there and ready to be consumed. If it's not there, if any of these things fail in between, then you can declare that something else is wrong and delete that volume and so on.
Yeah, so in summary, actually, we spent a lot of time and effort in sort of plugging these last mile holes, right? So making sure that all these sort of small little problems which could cascade into a larger problem, you don't end up there, and so your system overall is a lot more reliable.
Yeah, and the interesting part here is that these problems, when they show up, what you see, the symptoms of it is just that, hey, my pod is not running.
Right.
And it's like, you start from did the pod even get scheduled, and then you go from the Kubernetes master and then go to the minion and then figure out whether the pod moved and then say, hey, something went on. It takes a long time to actually go to the root of where the problem actually happened.
And in fact, in this case, for the longest time, we were looking for who did the delete.
Yeah, exactly.
Until we were like, okay, we don't see any delete operation. Let's go to CloudTrail.
If we created this volume, but the attach call failed, clearly someone must have deleted it.
Right. And actually the volume didn't show up on the console.
Yeah.
Right? So we were like, yeah, the volume is not there, which means it must have been deleted.
Yeah. But anyway, as I said, this happened twice, just twice. So hopefully this is not something that affects most people, and the problem, whatever it is, gets fixed hopefully sooner on the AWS side. So once we got past this, once we did this, we kind of, now we're in a situation where our cluster was running for a long time. It was capable of running for a long time. It was capable of handling the load that we were throwing at it. And then we ran into an interesting problem. Let's say that, on the system or on our cluster, we had two types of pods, system pods and user pods. When we started the cluster, we manually started these system pods first. Then we started these user pods. So at one point in time, the system pods were running, some user pods were running, and there were a bunch of other user pods waiting to be run. The amount of resources that we had on the system only meant a certain number of user pods were running. A lot of these were just waiting in the queue so that they get their chance to run. And again, at one point in time, all the minions or all the nodes on which these pods were running died.
I think it was like a spot price hike or something like that.
Yeah. Yeah, spot instances would be like a whole different amazing topic to do
That's right,
a webcast about.
Yeah.
But yes, maybe these were spot instances, that there was a spot price hike and all these minions died. The new ones were brought up and they booted up and then they became part of the cluster. But for some reason, when all these new minions started running, the Kubernetes master decided to run all user pods on these minions, and all the system pods in our system were kind of left outside waiting to be run. Now, and the fundamental reason for this, I would think, is that Kubernetes itself wasn't aware of system pods and user pods. This was like our concept that we had introduced, but for Kubernetes, these were just pods, and our pods had ordering guarantees or priorities, and these pods could move, but there was no way to enforce this ordering or priorities because Kubernetes did not understand the difference between these pods. So now we landed up in this interesting case where the user pods were running, they were finishing up their job, but the system pods, which are kind of there to consume the return status and clear up the resources used by these user pods, they were not even running. So again, there was some scope here for us to do to better architect our system, which we have done, but it got us thinking that we have this fundamental difference between the priorities of these pods, but the underlying infrastructure on which they are running does not know about this difference.
Right.
So what can we do about this?
So actually, an interesting thing over there is that Kubernetes actually has a limited concept called critical pods, which we were not using at that point. We are using that now, but along with that, so we explored different aspects like Kubernetes. Do we modify the Kubernetes scheduler, and do we add this sort of multi-level priority scheduling concept over there? Kubernetes actually can allow you to run multiple schedulers at the same time. So we could potentially have Kubernetes scheduler running along with our scheduler in parallel. However, I think it was like expedient from an engineering perspective to explore all the options over there. One of the options which she's going to talk about is using autoscaling groups and how sort of that avoided the problem altogether. I think it also gave us some interesting other benefits that she's going to talk about.
Yes. So as I said, the underlying infrastructure on which these pods were running did not know, or there was no way to kind of enforce some behavior on these underlying infrastructure, because for Kubernetes this was like one autoscaling group which had multiple nodes, so there was just one set of resources on which all the pods were running. So we started thinking along the lines of creating multiple autoscaling groups. So in AWS, you can create an autoscaling group where you can define what kind of EC2 instances should run in that autoscaling group. And one simple way to fix the problem that we had was to create two autoscaling groups, one autoscaling group for system pods and one autoscaling group for user pods. And with the way, with some launch configuration that AWS has, you can give tags to these instances. And once you have these tags, you can tell Kubernetes that these tags you can make those tags as labels, and then you can tell Kubernetes to run pods on instances that have certain labels. So you can have node selectors. Right. So when Kubernetes, when we were running a system pod, we were telling Kubernetes that, hey, take this and run this pod, and only run this on a node that has that is a system node that has a label called system. Or here's a user pod, run this on a node that has the label called user. So once you have this distinction, automatically Kubernetes was going to schedule them on two different sets of resources. So even if the instances died and came back up, it was guaranteed that our system pods would get the resources that they need to run, and all the user pods, even if there are hundreds or thousands of them, and only a few of them can fit into those existing minions, they will compete for a separate set of resources. So life was great. This way, we could separate our user and system pods separately, and have them run, or guarantee that they would run at any given point in time. And then once we had this, once we had two different autoscaling groups, we started thinking about more advantages, more benefits of actually using multiple autoscaling groups, which was awesome. Like now we were at this cusp of scalability and reliability. So we fixed the reliability part by having separate autoscaling groups, but we started thinking along the scalability lines, which is where the scalability aspect of running Kubernetes on AWS comes in. So because you have two different autoscaling groups, you could think about scaling these two different autoscaling groups separately. So you can imagine saying that, hey, I'll keep adding user nodes as I see more and more work to be done in the system. And for every 5 user nodes that I add, maybe I will add 1 system node. You can scale them independently based on some heuristic, some algorithm that you come up with yourself. Heterogeneous clusters. So you can again imagine each autoscaling group has its own launch configuration. Each autoscaling group knows, you can tell AWS what type of EC2 instances you want to run. So let's say that my system pods were very compute intensive. So I could use the autoscaling group that was used for running system pods. I could use C3.large or C3.extra large, compute heavy instances for running system pods. Whereas I could use like memory intensive or generic use instances for running my user pods. Again, heterogeneous clusters should just work in AWS. It's amazing. Spot instances. So as I mentioned earlier, spot instances would be a great topic for a separate webcast altogether. But again, in this case, because we have difference in the priorities, we have 2 different autoscaling groups, we can imagine that, hey, I want to keep my costs down. The maximum chunk of compute resources that I'm using in my cluster comes from my user nodes. So let me use spot instances for my user nodes, but my system pods can still use on-demand instances. So I know for a fact that they'll keep on running. My user nodes might go down depending on spot prices, but it's okay because I'm only going to pay 20% of the cost, which is awesome.
Right. And we actually do some more intelligent stuff where we can actually switch between spot instances and on-demand instances, even on the user autoscaling group. So that allows us to sort of not even have significant downtimes over there for user instances.
Yeah. As I said, spot instances is a great feature for a separate webcast. It's very, very exciting. So having mentioned all of these problems and the fact that we fixed all of these, we have fixed all of these one by one on our cluster, I wanted to give you a glimpse of this being in action. Here is one of our clusters that we have. As you can see here, 31 instances. This is one cluster. And one of these is the master. So this one, the last one that you see here is the Kubernetes master. The remaining 30 instances are minions. And if I just go into the other tab, which shows autoscaling groups. So I have 3 autoscaling groups for that cluster. This one, as you can see here in the name, you see the word user. This has 28 minions in it. This is where our user pods are actually running. This one, which has the word AX in it, you can even see it here in the tag actually. It's called AX tier. The AX tier here is a Platix. So this is where our system pods are currently running. So we have 2 minions dedicated for running our system pods, and we have 28 minions. You can see AX tier here is user. We have 28 instances which are used for running our user pods.
And it is variable actually. So the number 28 is 28 right now because we have loaded the system, and as the load goes down, the number 28 will go down.
In fact, the minimum number of instances is 1.
There you go. Yeah.
So you can when you just start off the cluster and there's nothing else happening here, there's just one user node sitting there for doing a user job. Right now, the cluster has several workflows running, which is why it has scaled up to 28. And as the load goes down, it will automatically scale down and can scale down all the way up to 1 instance. And just to show the same thing on the command line or something similar, I'm running this kubectl get nodes and show labels. So here you can see all these, all the nodes that are part of the cluster. You can see here the labels. So these are the labels that Kubernetes understands. So one of the labels on each of these nodes is called AX tier. You can see 28 of these should have the label called AX tier equal to user. 2 of them have the label called Aplatix, and 1 of them has the label called master. So this is the Kubernetes master. And if you look at when we run a particular pod, as I mentioned, we can use node selectors. So you can say that I want to run a particular pod only on a node where the label is ax.tier equal to user or ax.tier equal to Aplatix. So I have one example here on this other tab where you can see that we ran a particular pod called whatever default HTTP backend, and if you do a describe on this pod, it shows that it was run with a node selector called ax.tier equal to Aplatix. So this automatically runs on an instance where the tier is Aplatix, So it can only run on one of these 2 instances, this one or this one.
The best thing about our system is that actually our users don't have to worry about any of this stuff. Right? They just have to write their specification of what they want to run in a YAML file.
Yeah.
And we take care of handling all this in the background.
Yeah. Yeah, absolutely. So having said all of this, so these bunch of problems that we ran into, and this is where we are at today. We are able to run Kubernetes clusters on AWS, long-running Kubernetes clusters, which can actually scale up, scale down, do a lot of work for us. And after having fixed all these problems one by one, the scalability and reliability of the system is actually really good. So in summary, first of all, we started off with some long-running HCD tests to make sure that HCDs actually can stay up. We understood AWS limits and kind of worked our way around them, fixed them in whatever automation we could do. Volume problems one by one, hunted them down and fixed them, and then used multiple autoscaling groups for scalability as well as reliability. So as I said, having run all of these and fixed all of these problems, we are able to run clusters right now, and Platix clusters right now are actually really a lot of fun to work with. Which means that I'm really excited about the future. As Kubernetes becomes more and more mature, as we build on Kubernetes and improve on our own value propositions, the amount of things that we can do is phenomenal, and that makes me really excited about the future.
Right. Yeah. So actually, if you've heard, as you were going through the talk, you must be wondering, oh, these guys are not really happy about Kubernetes and AWS. Actually, that's completely the opposite. We love Kubernetes. We love working on this AWS ecosystem, and actually, we are very excited about contributing, building on top of Kubernetes, and seeing where this ecosystem takes us. So we definitely feel very excited about us being on top of Kubernetes and having a system which can provide value to the users on top of that, maybe make their lives a little bit easier.
Yeah.
So yeah, we are all pretty excited about it over here.
Yes, it's amazing to see the spring in Abhinav's stride when new Kubernetes release happens. He can't wait to get into the office and start hammering it with newer workloads and newer PVs and PVCs and pods and what have you.
All the new features. But yeah, so all those new features also do come with some caveats, right? And so when you bring in those new features, you also have to worry about what bugs are you bringing.
Yes.
in with it. So
Abhinav was super excited when dynamic storage provisioners happened, and
we spent a lot of time.
And 2 days after he tried it, he was really like, oh dear God, how is this going to work? But it can work.
It does work.
All right, so that's all we had in terms of the problems that we ran into and what we did for running Kubernetes on AWS at scale. And maybe I will hand this over to Scott.
Yeah. Well, thanks, guys. I got 4 questions that came through.
Okay. Oh, okay.
So first, Colin just asked a couple of minutes ago when your previous example about the ASGs.
Yeah.
But the third one was for the master, right? Was the third one for the master?
So currently on our cluster, we are not running master in an autoscaling group. The third autoscaling group that we saw on here on the console, on the AWS console that we showed, that was just one of the other autoscaling groups we use for kind of dedicated instances and so on. On the cluster that I showed, we did not have any dedicated instances, but it's possible to have them. Right. In theory, yes, the Kubernetes master can run in an autoscaling group of its own. We haven't run it as of now.
Okay, cool. All right. So next question. So did you guys talk about spot instances and whether did you already cover that?
We talked about spot instances briefly.
Okay.
So yeah, we on our Platix system we actually support using spot instances. When you go through our install process, we ask you a question: do you want spot instances? And the user can choose yes or no for that. And we definitely support all of that. The good thing about spot instances is that it's really cheap. It's like Shri said, about 20%, a fifth of the cost. The challenge with spot instances is that they can come and go. Right, and so when you are, let's say you're running a long-running deployment, right, and this deployment is actually your front face to some web service for your customers. Do you really want that running on your spot instances, or do you want that running on your on-demand instances? So there are these kind of questions that you need to think about. Spot instances are great for actually the workflows, right? There's sort of those one-shot containers that we run.
Right.
And so yeah, so we definitely support them.
Cool. I have 2 more questions here. So Jim asked, at a higher level, how does Platix Kubernetes on AWS compare with other Kubernetes solutions on AWS? Like if you guys are familiar with Heptio or Tectonic Core OS?
So we build on top of vanilla Kubernetes. So we the Kubernetes distribution that we use, we don't modify it itself per se. At the same time, we do, as Abhinav and me we were talking about earlier, we do bridge a lot of the gaps that Kubernetes has, and then think about like scaling or using AWS resources in a way that is easy, that is declarative.
Right.
So we build on top of that.
Right.
I for one haven't tried using any of the other Kubernetes solutions.
Right. So one of the things I guess over there is the following: is that I'm sure everybody who's in this ecosystem is working on making Kubernetes better, like CoreOS and others. So that's great. But what we are actually focusing on is not being just another Kubernetes provider, but what we are working on is providing a higher level application construct, where our system is actually going to be providing end-to-end DevOps workflows, a very integrated solution for running your containers, monitoring them, having cash as your dollars as your first class citizen, like Shri mentioned. So those are our real value propositions. Yeah. We happen to be using Kubernetes, or we happen to be running our stuff on top of Kubernetes. But our language is provides a lot more features. We have a sort of a different layer of abstraction that we are working on.
Great. Just a shameless plug, and then one more question about multi-cloud. Shameless plug is, Jim or anyone else, if you want to try Applatix, there's a playground link on our website, applatix.com. Splattered all over our website is a registration for a demo trial account. So, sorry, shameless plug. Check it out. Last question. So you guys have built on both AWS and Google GCP. Right. I know we're going to do another whole webcast on this, but any top line? We have one more question after that. Well, any top line on the differences between those two, or lessons learned?
I think Shri might have a little more idea.
So yes, we started off building our Applatix clusters on top of AWS specifically, and we spent a bunch of time experimenting with running Kubernetes on AWS. We've recently started supporting Google as well. One good thing that comes with Google is that on Google, a Kubernetes cluster is available as a first-class citizen itself. So you can just go to Google and ask Google's cloud to create a Kubernetes cluster for you. And the hope is that either these problems are already fixed, or that given that Google has probably spent a lot of time testing it. So these are actually problems that we as consumers of Kubernetes may not be able to see them. Okay. So yeah, I mean, right now a lot of the work on AWS is there because we deploy Kubernetes manually. On Google, it's just available.
It's just available. Cool. All right. One more question. Follow up. Does Applatix provide automated tools to migrate Kubernetes applications deployed in on-premise data centers to AWS?
So we don't have an automated solution right now, but our specification is actually very, very similar to Kubernetes specification. So if you look at our deployment specification and you look at a Kubernetes deployment specification, it's going to be very closely correlated. So I actually think that it should be fairly trivial. We've actually had people who sort of use our product and they go through taking a Kubernetes YAML and writing our YAML spec, and they find it pretty easy. So I think it should be fairly non-trivial. Fairly trivial.
Yeah. And the other thing there is that right now we would be more than willing to work with anyone who wants to actually make this happen. We've actually run several experiments in-house where we've taken stateful applications that have been deployed on Kubernetes that use MySQL, Postgres, and actually made their way onto AWS by actually migrating them step by step, looking at each of these one at a time. But we've been able to do it ourselves. Right. So we will be more than willing to work with anyone in any way or capacity to kind of make this happen.
And another thing is that the playground is the place where you can actually go and try that out. We actually have deployments over there that you can try out, right? Yeah. And then you can actually see the YAML specification for that. So that's definitely your first feel of Applatix, if you want.
Thank you everybody for joining. Really appreciate everyone's time and attention. Shri and Ahbinav, appreciate your time, and
thank you.
Hope everybody has a great day. Thank you. And another 3 weeks, next webcast, I think is probably going to be something around AWS and your story in deploying on both AWS and Google. So Signing out. Thank you. Bye
All
bye.
right. Thanks. Bye.
We made it out alive.
Yes.